It is, there are 4 free response. And remember, as I said, on the free response, I pull 1 from each exam. So for example, if I pulled this question, then I would get rid of some sections. I don't know what they would be, but I would get rid of some sections, for example, so that you only have two parts per question, but there are 4 total questions. Just keep in mind, so for example here, like if I did take this section away, then you would still need to find the total time, or at least you'd have to find the time that it was in order to find the maximum height. So just be aware of that. So you should practice all the free response. Don't try to guess which one I'm going to pick because you might not get it right. And then there are 40 multiple choice. So there are a total of 48. It's a little under. Let's see. Oh, there we go. Sorry about that. It is a little under twice the regular length, but you do have the full 2 hours. I don't expect time to be an issue for the exam. Particular questions, we could start with exam 4. That's probably the freshest, rawest, maybe? I don't know. Is it raw on you? Oh, okay. Any particular questions about exam 4? Or other exams that you want to look at?
For number 1, so like you know how for the OR problems we have to like the direction of which way the force is going. Does that matter on these?
Yeah.
Like giving you a positive and negative?
Yeah, of course. Yeah, so it does matter on this when you're finding the net torque, that you do have to know the sign of the torque. Because on this one, if you didn't get the signs right, you would have gotten it wrong. This force right here causes a clockwise torque, so it's a negative. And this force, which really, it's just that component of the force that causes the torque, that causes a counterclockwise torque. So that torque is going to be positive. Okay? Because I will say on the multiple choice, I said this in class, but let me just be clear. So, for example, if I were to give you number 3, I did in fact give you number 3, that I would just give you a different shape. All right, and then I ask you to rank the moments of inertia. I would take the same question, but change it so that it's a different question. In fact, if you go back and look at past exams, almost every exam has a question like number 3, except it just has a different shape, where it might have a square, I think I gave in one exam, or I think one exam I gave a star, or in one exam I gave a this or that, and have to rank the moments of inertia. But the idea is still the same. Or on number 4, I might give you this, but with just a different figure and different dimensions. So it's really just the numbers that are changing. Or number 2, I might give you this question, but instead of bringing her arms inward, she'd be putting her arms outward. And so it changes the answer to the question. Let's look at some other examples of how it might change. Number 5, I might change, but just by changing the numbers, say 4 and 8, or making it an angular momentum problem. That is a problem where I say that Li is equal to Lf, but it could be a little bit different. I might make it so that it's not a perfectly elastic collision, so that instead of having I1 plus I2 times omega final, that I would have I1 omega final 1 plus I2 omega final 2. And physically what that means is, in this problem, the two things stick together and they rotate at the same rate. But if I don't have them rotate at the same rate, then they can have different omegas. That's not a great example. That doesn't usually happen. But number 7, I could give you a different figure and ask you to rank the torques or tell me the latest, largest or smallest. So you'll see the same questions, and you'll probably recognize them as questions that you had on your exams, especially if you've been practicing those exams over and over, but they will be different. So that is a caution for you, that if you think, oh, you know the answer because you remembered it from the previous exam, then make sure you read it very carefully, because it has changed. Every question is different. So that means that the answers are going to be different too. Okay?
In terms of the free response, like I know, like, you could change, are you gonna change the graphs? Cause like, I know how if you ask
Yeah.
for something in a V and T graph, it's gonna be different if you ask for it.
Yeah, so like for example, where we have this graph, our exam one, that's what I would do is I would give you a different graph, but it would still be a position versus time graph, and I would still ask you the same thing. So the free response are not changed hardly at all. Just numbers are, like in this case, I would change the graph. Let's see, what else? Look at those free response. This would just be changing numbers. Yeah, changing numbers. I wouldn't change anything about it except for the numbers. Okay. That's true on all of these. Yes. No, I didn't even change the shape. I don't remember if I gave you this question, but I didn't, on the free response, I didn't change the shape either. Everything's still the same except for the numbers. Okay. I want those free response to be perfect, which I'll do really well on those. So practice those free response until you know them really well. I will say, that you've had these free response and they are online. They will be different because of the numbers, but if I find you looking at the questions online or on your phone or any sort of academic dishonesty, that is a 0 on the exam. Okay, plus a loss of your integrity, and you have to go through the whole thing with the university, and if you're pre-professional, that basically kills your chances of getting into a professional school. So just don't be honest. It's better to get a bad grade than to be dishonest. Your integrity is worth a lot more than a good grade. Okay, what else? Particular questions you want to look at? I can scroll through the exam, so let's just take a look. We have kinematics questions. I would expect to see those. Graphing questions, of course you'll see those. This is chapter 1, so we had some order estimates, order of magnitude estimates. Dimensional analysis, significant figures, you need to know your standards. So for example, on these, the way that I would change them, number 6, I could say which of these is the standard for the second, or the meter. And actually those are here, the frequency of the cesium atom, that's for the second, and for the meter, it's the constant speed of light. Okay, so just because it says kilogram, know that it could be something else, like second or meter, so know all those standards. Some basic trig stuff. I don't usually put basic trig stuff in the final because it comes up in all the other questions, FYI. But you will see some unit conversions like we have in number 11 or number 10. So make sure you know how to do your unit conversions. I think we're all on board with that now. And then some kinematics. You'll have a couple of one or two kinematics questions. You will see some questions like this. This came up a couple of times where you have to analyze velocity and dimensional and position versus time graphs. You will see a number of these 1, 2, 3, 4 questions and asking which of those are the correct statements. All right, graphing questions. You have to determine velocity, acceleration, or displacement from those graphs. Okay. Any of these y'all want to look at more closely? Are y'all brain fried from the day? Yeah? Okay. Yeah, Mariah? There's, one from each exam with 2 parts per exam. So I don't think you were here when I said it. Let me just repeat it because it's important. So if a question has more than 2 parts, I've just eliminated a couple of those parts so that you only have 2 parts. So there are a total of 8 questions, free response as usual, but there are 4 separate questions, each with 2 parts, and 1 from each exam. So you will see 1 from each exam. Okay, vectors and 2-dimensional motion. And inclined plane, you're going to see 2 or 3 inclined plane problems, either on free response or multiple choice. They come up quite a bit. They're kind of important. More projectile motion in this. Here's some more of those position versus time graphs. You need to be able to analyze just stuff about projectile motion, basic facts about it. this question I took off the exam, so you won't see it at all. Vector stuff, graphical analysis of vectors. There are 2 questions here, so you can bet you'll have at least one of those. And then some other quantitative questions where I ask you the sum of these vectors or the components of those vectors. Now stop me if you want me to do some of these. You will have some Newton's law problems where you have to either know what Newton's laws are, like number 14, or apply like Newton's second law, or in some of these are applications of Newton's first or second law, number 11 and 12. As I said, you will have some inclined planes and some 2-dimensional, like this one, number 16, but it'll be a little bit different, but still very similar. You'll be able to identify it. Okay, now stop me if you want. Number 19 is on there, of course. I like that question. You will see friction. Friction comes up a bunch on the exams, so just be aware that it'll be there. All right, that was exam 2. You want me to go back for something? Exam.
I have a question.
Yeah, go ahead.
Questions about the what was it? No, which last one we took?
4? Mm-hmm.
I just didn't. I wanted you to go work number 17 and 19.
Okay. Okay, yeah. So number 17, this one with the barometer. Number 17 is a barometer, by the way, not a manometer. I know it's a barometer because this is a vacuum. So I want to know what P1 is. P1 is equal to P2 plus or minus rho GH. Turns out that the plus or minus doesn't really matter because P2 is equal to 0, so I'll get rid of that. And I don't have a negative pressure, so I'll just leave that off. So P1 is equal to rho times G times H. Now, I can calculate that that P. Rho is 1,000. That's the density of water. That's on your equation sheet. G is 10 meters per second squared. H is what I'm looking for. And probably the mistake that you made is that you put in 1 right here, because after all, it does say that the pressure is 1, but it's 1 atmosphere. And an atmosphere is 1 times 10 to the 5th pascals. 1 atmosphere is equal to 1 times 10 to the 5th pascals. I think that conversion is on your equation sheet, but you just had to know to use it. And then I solve that, so I have 100,000 divided by 10,000 equals H. So H is equal to 10 meters. Okay. If you remember, we said that the very first barometer was a wine barometer. The guy used a wine in the barometer in order to measure the atmospheric pressure. And so the height of that column was 10 meters, which is about 30 feet. If you think about it, that's a big old barometer. In fact, it's really difficult to make this into a true vacuum when you have such a big column of water. There's a good Veritasium video. I'm not sure. Y'all watch Veritasium on YouTube? Oh, losers. Man, y'all need to watch Veritasium. And we've watched some in class. But anyway, there's a good video where he tries to build a 10-meter column. It's darn near impossible. Anyway, so the H here is equal to 10 meters. By the way, what if I filled this thing with mercury? What would the height be? Somebody said it. I know. It's a standard pressure, a standard measurement of pressure, a mercury-filled barometer at 1 atmosphere. 760, yeah. Who said that? Yeah, that's right. So 760 millimeter, you might have seen that. Our 760 torr is called as atmospheric pressure. That means that if you fill that thing with mercury, which is, much more dense, it would only be about 7.5 centimeters, about that tall. That's what they use in the old blood pressure measurements with the column of mercury. All right. And then you said 18 or 19?
19.
Yeah, 19. So 19 is just plugging in the right numbers. So I have my stress, F over A, is equal to the Young's modulus times my strain, which is delta L over L. And I want to know what is the increase in length. That is, I want to know what delta L is. So I have F divided by A times L over Y. So if you got this one wrong, you might have made a mistake with your order of operations in your calculator. I find students often do that. So make judicious use of parentheses, or do them in steps and write out the numbers on your paper along the way. So this will be 1960 times the length, which was 2 meters, divided by the area, which is 7.1 times 10 to the minus 6 square meters. No conversions there, thankfully. And then the Young's modulus for copper is 11 times 10 to the 10th. I just got that from right here. And then that gives me my delta L. I think it came out to be, I don't even remember what the answer to this was. Do you mind know? What is it?
What, I got 0.5 out there. That was right.
It's 5. Yeah, so you get 0.005 meters there. But notice they're all in millimeters, so I have to move this over 3 spots to get the answer in millimeters. Remember, 1 meter is 1,000 millimeters, or 10 to the third millimeters. So that's where that 3 comes from. I have to move it 3 spots. Yeah. Oh yeah, gosh, a lot of people miss this one. So you will see Archimedes' principle on there. There are a couple of questions here. You will see it. And I have a rectangular boat. Note that I give the length and width, but please note that the volume is length times width times height, or depth. So I'm missing that third dimension for the boat. If I want to find the depth that it's submerged, my boat is like this. I know that there are 2 forces acting on it. There's the weight of the boat, and then there's the buoyant force of the boat. And I know that in order for it to be floating, that the buoyant force has to equal to the weight. So my buoyant force is equal to rho times V times G. That's the density of the fluid, volume of the object, times G. And then the weight is equal to 500, or just M times G. My G's cancel. And then I'm looking for the volume of the boat, the volume of my object, the submerged volume. That's going to be the mass of the object divided by the density of the fluid. That's 500 kilograms over the density, which is 1,000 kilograms per cubic meter. So the volume of the object is 1/2 cubic meter. Which you might have put 1/2, but you know that's of course not the right answer. I would say that the volume, which is 0.5, is equal to 2 times 1 times the height of the boat. 2 times 1, and then I find that the height, or the depth that it's submerged, is 0.25 meters. So A was the right answer. As usual, I go through and I make the mistakes that I know students make, and I'll put those as answers too. So just because you get an answer doesn't mean it's the right answer. Just a warning, not a warning, but just, I don't know, advice, I guess. Y'all want advice? Yeah. Write stuff on the exam, draw pictures, write out your knowns and your unknowns. I see a lot of students, usually students that don't do very well on their exam, that just don't write anything at all on their exam. I know what they're doing it in their calculator, and it's just, you can't think in your calculator, but if you write stuff on the paper, it really helps you to think about what's going on. So I really do encourage you to do that. Draw pictures. Even if you come to a problem that you have no idea about it, just start writing stuff down. Write down, go through the problem and read it, and write down the knowns and unknowns, and then draw a picture to help you think about what's going on, and then begin to think about how to get to the solution. You should have plenty of time. I mean, you don't have time to go take a smoke break or anything, but you have plenty of, I don't smoke, right? You don't smoke? Yeah, actually, you shouldn't. It's very bad for you. But anyway, you should have plenty of time to take the exam. So use that time to write stuff on your exam. All right. Any others on this exam or other exams? Yeah, a lot of people missed that one too. The reason they missed it is because it was a little bit different than the one we did in class, right? Though there was a free response that was similar, where I asked you to find the total energy, and that one was just like what we did in class. But this one was a little bit different, where you had to find the total energy. I'm going to draw a ball. That'll represent my mace. It goes up. It'll come back down again. And I want to know, what is the total energy here when it's at a height of 2 meters? And so that total energy is equal to the rotational kinetic energy. as the thing's rotating as it goes up in the air, plus any gravitational potential energy that it has gained. And so that's going to be 1/2 I omega squared plus m times g times h. As usual, you'll have to find I. That'll be on your equation sheet for a bar, 1/12 mv squared. Be careful on this. Make sure that you recognize that b is not the radius. I mean, a bar doesn't have a radius anyway. It's the length, which is 2 meters in this case. I'll come back to that. We'll talk about it. Anyway, so that's 1/12 times m, which is 1 kilogram, times b, which is 2 squared. So is that right? Yeah, 4/12, 0.33. That is my I. I'm going to write it as 1/3 actually. So 1/2 of 1/3, and then omega, I'm told, is 6 radians per second squared, plus m, which is 1 kilogram times 10 times the height, which is 2 meters. That's from right here. The 6 plus 20 are 26 joules. But this, if you got this wrong, which a number of people did, that was why, that you probably weren't considering the gravitational potential energy. Which I understand wasn't an equation on your sheet, right? But I mean, y'all know gravitational potential energy, mgh. I think that's just something y'all know. All right. What else? Yeah, you'll see that, I'm pretty sure. Let's see, that would have been like number 20. Yeah, I think that's really the, oh no, there was one in the free response. So let's look at both of those. So here, boy swings a 2 kilogram stone in a horizontal circle with a radius of 2 meters, and it breaks when it rotates at 2 radians per second. So if I had no idea what was going on here, first I'll just start by writing down the things I know. The mass is 2 kilograms, the radius is 2 meters, omega is 2 radians per second. I can pick off those things. I can tell from the units that those are the values that I'm looking at, and plus just how it's described in the text. And I want to know what is the tension. And then I can draw a picture. It doesn't have to be a pretty picture, but I have this thing that's rotating in a circle like that. And I know that at any point that the force right here is the tension that's pulling, the string is pulling that object, and that tension is equal to my centripetal force, which is mv squared over r, or in this case, it's easier to think of it as m omega squared r. I say omega squared because I'm given omega. Of course, you could figure out what v is. V is equal to omega r, and then you could use this equation, but it's easier just to take that second one. And so then my tension is m, that's 2 times omega, which is 2 squared times the radius. Oh, they're all 2. So 2 times 4 is 8 times 2 is 16 newtons. Okay? Let's look at that other one.
What exam was that?
That was exam 3, I think. Yeah. Let's look at the free response for this. You know what? I'll give you a pass. Number 4 is not on the exam. So if you see this help session or since y'all are here, that's like your little gift. Okay? Is that okay, Austin? I can still work it if you want. No, I'm just joking. It's not on the exam. So just know how to do that other one. All right. If you want to work it later, we can stay after. But not on the exam. Other particular questions? Teresa? Yeah, so roughly there are 10 multiple choice per. With the exception of chapter 4, there are slightly more with chapter 4. So you might have like 9, 9, 9, and what would that be, like 13 or something like that. Okay? It's slightly more for chapter 4. But it's mostly evenly distributed. And then 1 free response from each exam. Is that all? Yeah. Yeah, what was I doing? So this is exam 3. You sort of want to skim through it. Oh yeah, so you have, this was work energy theorem. That came up a couple of times on exams. I think, yeah, on this exam. So you'll see work energy theorem, this one or like one of the others. Gravitational potential energy here, or this is really just a potential energy at the top equals kinetic energy at the bottom. Units, y'all know how to find basic SI units. You write down the formula, MGH, and you put in the basic SI units for each variable. You also see elastic potential energy. I think that came up a couple times. Yeah, 4 and 5. So when you see multiple problems for a topic, then you'll know that that topic will be on there. In fact, I would say every topic is on there with the exception of those very basic things that we did in the beginning with trig. But you will see dimensional analysis, and you will see, I think sig figs are on there. I think there's a standards problem. I don't remember. I write a bunch of problems and then I pick some out. But this is another conservation of energy and work energy theorem. It's just calculating the work. Y'all pause me if you want to work through some of these. And then we move to momentum, linear momentum. That's like number 9. I find it really useful in questions like number 9 to draw a picture. So for example, I would draw a picture here where I have my 1 kilogram block that's traveling to the right at 3 meters per second, and it collides with a 2 kilogram block, which has 0 velocity. And then that would be my first state. And then my 2 kilogram block now has a speed of 1 meter per second. And I want to know what is the speed of my 1 kilogram block. I find drawing pictures like that really helps me. Well, because if this thing ran into the 2 kilogram block, there's no way that it's going to go to the left, right? You should see that. Like, it's just not possible for this one to move to the left. It has to move to the right. But you're right. I didn't state that explicitly in the problem. I probably should have, but it's not really possible for it to move to the right. As usual, if you ever have any questions like that, like you're just not sure about some of the wording, or you can ask me a question. I'm not going to tell you anything that I wouldn't tell the whole class, but I can clarify some of the language that I use. And if it is something the whole class needs to know, then I will tell the whole class. All right? Sometimes students, when they ask me questions, I'll just sit there and they ask the question and then it's like, oh, right. And I don't say anything at all, but somehow it helps them to talk through it. But you don't need me to talk through it. You can talk through it on your own, inside your head. All right. Another conservation momentum problem. This is a Newton's second law, F equals delta P over delta T. There's a couple of those, 11 and 12 right there. And then just about elastic and inelastic collisions. Conservation momentum here. I want to just know which statement is true. So on something like this, I could give you the same scenario, but give you 4 different statements. So read this and think about what is the underlying principle. That is that the angular momentum, or excuse me, the linear momentum, pi, is equal to the final momentum, that those momenta are the same. And then also something that came up was that p is equal to m times v. So the one with a small mass had a big velocity, and the one with a big mass had a small velocity. Those are sort of the underlying principles. And so I could take that question and write different parts that are assessing those underlying ideas. Great way to think about or to look at how I might change questions is to look back at past exams. Because that's what I've done in past exams, is I've taken those students' exams and I've rewritten the questions to come up with some new questions. Not all of them, but some of them are, or that's how I came up with them. So it is useful for you to practice the past exams. All right, then we got into chapter 7, angular quantities and centripetal forces and angular or rotational kinematics. All right, and then chapter 4, I think we've already been through chapter 4, or exam 4, excuse me. Yeah, on in this one?
Yeah, number 3.
Number 3? Yeah, so first of all, I want to know the angular momentum, A. That is L is equal to I times omega. So I'm just looking at the disk right now. So I for a disk is 1/2 mr squared. So L is equal to I, which is, that's 1/2 of the mass, which is 2 times 2 squared. It's 1 times 4, so it's 4 times omega, which is 3. So this is my omega. I just calculated my I, that's equal to 4. Did I do that right? Is it 12? I don't remember that being the answer. Oh, I have the mass wrong. Thank you. Yeah, so this should be 4, and so that's 8, so that's 24. What's that? Kilogram meters squared per second. All right. So that's my total angular momentum of just the spinning disk. But then I put this object on the edge of this disk, and I want to know what is the total moment of inertia. So that's going to be equal to I of the disk plus I of the particle. And that's what I'm dealing with, a particle here. And I of the disk we've already found to be 8 plus mr squared, where that's going to be the mass of the particle, which is a 2 kilogram mass, times the distance r, which is 2 meters. So that's going to be 8 plus 2 times 2 squared. So it's 16 kilogram meters squared. That's the total moment of inertia. That's just where I'm adding up the moments of inertia for 2 different objects. And then finally C, which is sort of everything we're building up to here. What is the final speed? So that's Li is equal to Lf. Angular momentum is conserved. The initial is equal to the final. My initial angular momentum I've already found, it's 24. Though if you got part A wrong, I didn't count part C wrong if you did it correctly. And then Lf is going to be IF times omega F. I've already found IF. That's equal to 16 times omega F. So omega F is equal to 24 over 16. What's that? 3 over 2, 1.5. I think that was in radians, wasn't it? Yeah. Okay. I don't think there aren't really any tricky unit things going on, but in this question, if it was given in revolutions per second, I would have had to change that for part A, but I'm pretty sure I don't have any tricky unit stuff going on regarding these, but you'll never go wrong with SI units. So if you ever have a question, it's always better to just convert to SI units. Okay?
What was the answer for number 2, like on the multiple choice?
On this test?
Yes, sir. Yeah.
Oh yeah, so she has her arms out, she brings them in. When she brings them in, she goes faster, right? Now, her angular momentum will always stay the same, unless there's some outside torque, which there's not in this case. So I can get rid of this one, this one, this one. It's either V or E. Because she goes faster, because omega goes up, that means that her energy will increase. We had this question in a concept test, if you recall. L is equal to I omega, and then kinetic energy is equal to 1/2 I omega squared. So when she brings her arms in, that means that her moment of inertia decreases. It decreases by a factor of 1/2, say for example. That means that omega goes up, let's say, for example, by a factor of 2. Whatever one does, the other does the opposite. And so if I have a 1/2 here and a factor of 2 here, then that means I have a 2 over here because the omega is squared. So if I double it, I'm actually quadrupling the contribution, the increase, where I only have a factor of 1/2 for I. So if she speeds up, she's going to have a greater energy. Okay? All right, I think we'll stop. If y'all have additional questions, I can answer them afterwards, but y'all look like you're ready to go home. Have a good weekend. Practice, practice, practice. Other exams? Is organic on Monday?
Yes, at 8 in the morning.
Yeah, you're welcome. It's been that way since before the beginning of time. So many students have done just fine on organic and physics on the same day.
For the extra credit grade, what
Yeah.
about in terms of